Hello everyone. I've had a few requests to do a video about star life cycles, as I know this can be a bit of a tricky topic at Key Stage 4 in physics. So here we go. And I thought, given the nature of the subject, I'd try something a little visually different and give it a bit of a space feel with the black background. In any case, the key to this topic is remembering the order or the sequence of events that you get. Now, let's look at the picture in the top right corner. The picture that I've got in the top right corner is actually of something called the Crab Nebula. And in fact, just for reference sake, I'm just going to put that name. So that there is the Crab Nebula. And that Crab Nebula is thought to be a cloud of gas left over from a supernova as far back as 1054. Now, this is our starting point. We've got this cloud of gas called the nebula, and this predominantly contains hydrogen. So we're going to just make a note of that here, that Crab Nebula, or the word nebula essentially, means a cloud of gas mainly containing hydrogen. Now, gravity, we know, is an accelerating force. Now, when gravity acts upon this cloud of gas, it pulls it all together into one central point. Now, this central point would become extremely dense. So if I just, with a little yellow, for example, just put a bit of a cross at the area we're talking about. So we're talking about this central part there. So gravity is acting on this cloud of gas, it pulls it together into that central point. Now that central point, if we're saying that everything's being pulled because of gravity to that centre, what we find is that over time the temperature starts to increase, and this dense centre forms what we call the protostar, and that is our real starting point in this story. So what I'm going to do is essentially draw a diagram to represent the different stages you need to know about in the exam. So let's start by drawing the protostar over to the left. So let's draw it as, now these aren't the best drawings at all, but I thought rather than use diagrams, I just wanted something quick, something visual that you might be able to draw yourself. Now, it's not the best drawing, but this is meant to represent an early star, a protostar. It's just where we've got this cloud of gas, essentially just condensed. And this, so we'll just label that. This we're just calling our protostar. Now, this centre, this protostar starts to get hotter, it gets bigger, and over time we form a new star. Now, under these conditions, so we'll just make a note of that in fact. So we're going to increase the temperature, and we're going to increase in size. Now, over time we form the new star. Now, under these conditions, nuclear fusion happens in the core. By core, I mean the centre. So we're getting nuclear fusion in the middle of this protostar. Just a little reminder, nuclear fusion is when two smaller nuclei fuse together to make a larger nucleus. Now, in this case, we actually have two hydrogen atoms fusing to make a bigger helium atom. So let's just quickly add that to the diagram. So what we'll have, it's just a note here that we get nuclear fusion. We have H, symbol for hydrogen, fusing to form He, the chemical symbol for helium. Now, in my previous physics videos on forces, I've said that every force has an equal and opposite one, opposing motion. The same is essentially true here. Now, from fusion, we release a lot of energy. And if you imagine this energy wants to push outwards, so from this protostar, if we just imagine, just draw this in blue for a moment. If we imagine this energy wants to push outwards, then what we actually have is the force of gravity pushing back in. Now this means the forces are balanced, and so the star is actually stable, and that is what we want. This is what we call our main sequence star. So that's the next thing we're going to draw in this almost like a flowchart diagram. So we go from protostar to what's called a main sequence star. Again, just a very quick sketch. Main sequence star. Now this main sequence star, as I said, so this is a stable star. This is when the forces that are pushing outwards as a result of all this energy that we're releasing from fusion is balanced by the force pushing inwards, the force of gravity. So we've drawn the main sequence star in place, and at this point I just want to reinforce the idea that these forces are balanced, and this stage can actually last for billions of years. So we'll just add that very quickly on the diagram, that this particular stage can last billions of years. So our own sun, for example, is in this particular phase. It's a main sequence star. Now our sun will have existed for about 10 billion years in total before it starts to die. And there's me thinking my 15-minute videos are a little long. So now we've pretty much come to a crossroads. See, what happens next depends largely on the mass of the star, or how much material it physically is made up of. So stars about the same size as our own sun follow one path, and those that are much, much bigger take a different route. So let's consider the route for those that are the same size or smaller than the ones of stars compared with our own. So what I'm going to draw now is something called the red giant. So we'll just put this red giant in place and then I'll explain what we've got. So we've got here, again, not the best sketch, but you hopefully home can work out where I'm going with this one. Just draw a little bit around the edge there. There we go, that's my best attempt. And this we're calling a red giant. Now this route you only take if the star is about the same size as the sun. So we're just going to make a note of that because that's really, really important. So this route that I'm describing now is if the star is roughly the same size of our sun. So this, I said, is called a red giant. So as our main sequence star starts to cool, it expands and forms this big red ball, this red giant. So I'm going to draw some arrows on this body because over time the outer layers start to break away from it, forming what we call planetary nebula. So as you can see, we kind of get back to the beginning of our story in a way. So these outer layers come away from this red giant and form planetary nebula. Now, if you imagine the outer layers being lost, all you have left is an incredibly hot white core, and this we call a white dwarf. So once our main sequence star cools and then starts to expand, we form the red giant. Then after the red giant, what we end up with is something called a white dwarf. We'll just draw that as a little white circle there. We'll label this as white dwarf. And it's this hot, it's very hot, very dense centre, this dense core. Now when this cools, what we form is a black dwarf. So basically, stars the same size as our sun or smaller cool, expand, they form a white dwarf, and then finally they form a little black dwarf. And there's half of the story. Now let's consider the other path that stars can take. Now only the large stars, those with mass with quite a large mass rather, get to experience the characteristic supernova that you might be familiar with. So if we go back to our main sequence star, cooling and expanding, but this time what we're saying is it expands much greater and it actually forms what's called a red supergiant. So let's put that in place there. So we've followed that first path. Now we're going to go down a different route. We're going to say from the main sequence star, instead of going to a red giant, let's draw a bigger arrow just to make it really clear. What we're now going to get is this thing. So I'll just draw this really quickly. Again, just a very rough picture here. Not very specific, but you hopefully get the overall gist of where I'm going with this. And this we call a red supergiant. So this one here is a red supergiant. And this we only get when the star is bigger than our own Earth. So before we had where the star is the same size of the sun, this time we get this when the star is bigger than our sun. So we've got this red supergiant. And this is something extra to be aware of. Many argue that our universe started with the Big Bang and that over time hydrogen atoms fused to form heavier ones, to form our heavier elements like iron. Now this happens in the core of dying stars. It actually happens in the core of these red supergiants. They are so big that they're able to fuse nuclei together. So we're just going to make a point of that also, because that's important. So that these red supergiants, what we're able to get is fusion of heavy nuclei, that red supergiant. Now, then, and only then do we get our supernova, an explosion so powerful that we release all these heavy elements into the universe. So that is really our next step. So from this red supergiant, what we get is this explosion. Now this isn't going to be the best picture at all, but this is just going to represent an explosion here. This is meant to be our supernova. Now, the gravitational forces acting here are very strong, and the core of what was our red supergiant gets crushed down as such into a small neutron star. Now this is a very, very dense phase of this star's existence, and actually it spins or rotates very rapidly. As it does, it sends out these pulses of radio waves. We know this happens because here on Earth we can actually detect them. So let's just add that to the diagram. So what we've got essentially is from this supernova. In fact, I'll just shrink the screen a little bit more just to put this in place. I'll just move this up a little here to the side. So what we've got from that supernova is something called our neutron star. I'll just put that in place there. This is our neutron star. So just to reiterate, it's the core of the red supergiant that after the supernova gets crushed down because of gravity, and it comes into this very, very dense body that's spinning and rotating very, very quickly. That's our neutron star. Now, should those forces of gravity be so great and our central core of the star had been so big, then we end up crushing material so compactly that we form what's called a black hole. So we've got there about the neutron star, but we can end up with what's called a black hole. Now, scientists say that they are infinitely dense and that the gravity is so strong in a black hole that nothing can escape. Now, I find that fascinating because even though we cannot visualize them as such, we know that black holes exist. We know how they're born, where they occur, and why they exist in different sizes. And we even can surmise as to what would happen if you fell into one. So that is pretty much it. We've talked about stars that are the same size or smaller than our sun. For stars that are bigger than the size of our sun, they form red supergiants. That's followed by a big explosion, the supernova, and from the remnants of that, you get either a neutron star or, if the core is so dense, a black hole will form. Okay, hope all that helps.